Welcome, everyone, to ChemTutor Manitoba. Today, we're focusing on calculating enthalpy changes for reactions using Hess's law. By the end, you should be able to use formation enthalpies and reaction steps to find ΔH for a target reaction. Enthalpy change, ΔH, measures heat absorbed or released at constant pressure. We can determine ΔH for a complex reaction by combining known reactions whose enthalpies are tabulated. This is powerful when the target reaction is hard to measure directly. Hess's law states, the enthalpy change for an overall process equals the sum of enthalpy changes of any set of steps leading from reactants to products. In other words, enthalpy is a state function, independent of the path taken. We'll use this to build the target reaction from known steps. One common route uses standard enthalpies of formation, ΔH degree F. The formula is ΔH degree reaction equals sigma nu P ΔH degree F, products minus sigma nu R ΔH degree F, reactants. Nu are stoichiometric coefficients. Be careful with physical states and coefficients, they matter. I'm introducing a simple technique to calculate the unknown enthalpy change for any step in a reaction sequence. Because enthalpy is path-independent, the total ΔH from A to B is the same no matter the route. In the figure, A goes to B either directly or via X and Y. Both routes have equal overall ΔH. The cycle diagram shows two paths, clockwise green and counterclockwise purple. The sum of ΔH values along the clockwise path equals the sum along the counterclockwise path between the same start and end points. When combining reactions, use three rules. Reverse a reaction, change the sign of ΔH. Multiply a reaction by N, multiply ΔH by N. Add reactions, add their ΔH values. Direction matters. If you traverse a step opposite to its arrow, subtract its ΔH. If you go in the same direction, add it. To find the unknown enthalpy for the step XY, isolate it from the cycle using the equality of paths. Rearranging gives ΔH2, XY, equals ΔHR, a B, minus ΔH1, at X, minus ΔH3, YB. Look at the worked example here. Find ΔH degree F of liquid methanol, CH3OH. The target formation reaction from elements in standard states is C graphite plus 2H2 plus 1/2 O2 CH3OH. We're given three reactions: combustion of methanol, combustion of carbon, and formation of water. In a cycle, the sum of ΔH going clockwise equals the sum going counterclockwise between the same start and end points. We'll use this idea implicitly in our worked example. Double the water formation reaction to make 2H2O. Pause the video and try to find the answer. Sum the enthalpies. ΔH equals plus 726, plus, minus 393, plus, minus 572, equals minus 239 kilojoules per mole. Therefore, the standard enthalpy of formation of CH3OH is minus 239 kilojoules per mole. Concern about incorrect stoichiometry, especially oxygen fractions. Forgetting to flip the sign when reversing a reaction. Ignoring physical states. ΔH degree depends on liquid, gas, and solid states. When you do the calculation. Key takeaways: enthalpy is path independent. Use Hess's law by reversing, scaling, and adding known reactions. Verify with cancellation, then sum ΔH values. See you again.